Hey everyone, today I want to talk about a project I built while working at the Accelerator for Princeton University, a distributed web crawler that can handle multiple platforms with the same code base. Now, web crawlers have been around forever, right? So you may be wondering, why build another one? Well, stick around because this one's different and I'm going to show you exactly why. So here's the thing, most crawlers are built for one specific job. You want to crawl websites. But build a crawler, need to pull data from Telegram, build another one. YouTube, yet another crawler. And every time you do this, you're duplicating so much code. The same logic over and over again, just slightly tweaked for each platform. It's inefficient, it's hard to maintain, and honestly, it's frustrating. Plus, when you're doing research, you end up with data in completely different formats. And, that just creates a lot of additional work. It means the ETL process becomes a nightmare of transforming different formats before you can actually analyze anything. So I knew there had to be a better way. And that's why I created the distributed crawler. Now, it could probably do with a better name. The idea was it would scale. The core idea was simple though, build one framework that could crawl multiple flat platforms without rebuilding anything from scratch each time. The goals were pluggable architecture, so you could add new platforms easily, support for multiple cloud backends because not everybody uses the same infrastructure, extensible configuration so researchers could customize it for their needs and keep the footprint as small as possible. It sounds ambitious, right? Well, let me talk you through how we actually built it. So I started with Telegram, and let me tell you, this was an adventure. To properly crawl Telegram, you need SIM cards, multiple SIM cards. So picture this, I've got a SIM farm sitting in my office and I'm trying to connect the crawler to multiple Telegram API backends simultaneously. It wasn't pretty, and it was definitely an interesting experience trying to get it to work, but we got it working. Using distributed techniques, we achieved really effective scalability. The crawler could connect to multiple accounts to pull data in parallel. Now, here's where it gets tricky. When you're crawling multiple channels across different accounts to build a complete picture of what's happening on Telegram, you need to ensure your data is both accurate and complete. We're talking about manual verification checks, checkpoints throughout the process, and checksums to verify data integrity. Because the last thing the researchers need is incomplete or duplicated data. And then there's the multimedia problem. Every social media platform is packed with images, videos, files, you name it. So we built a system to identify and download different file types, process them automatically, extract the metadata from the files themselves, and run OCR on images to pull out the text. Why? Well, that's a good question. Because researchers need to search through this content. If someone's looking for posts about a specific topic and that topic is mentioned in an image, we need to be able to find it. This gave us proper search context and lookup capabilities for multimedia content. Okay, the first phase of the development is over. So at this point, I had a working Telegram crawler, but I wanted to be able to prove the pluggable architecture actually works. So it was time to add YouTube. And here's where things get interesting. I used Claude Code to help me refactor the existing code base. We needed to create a more generic interface that would let us plug in different social media endpoints. And Claude Code was super effective here, helping me restructure everything properly and in a much quicker time than I would be able to do if I was just adjusting the code myself. Then, leveraging the YouTube API libraries and some of the new interface, we built out the YouTube layer. In some ways, this was easier. There was no SIM farm required, but the YouTube data API is pretty restrictive. You're limited in both what you can access and how much you can collect. Fortunately though, we were working for Princeton University, so we applied for and got access to YouTube's research API. It's basically the same as the standard API, just scaled up for larger volumes. Simple, right? But here's the catch. Even with the research API, you do not get access to the actual video content, transcriptions, unless you own the video that you're trying to get the transcription for. And so that means you get titles, descriptions, engagement metrics, comments, but not the video itself. And this isn't necessarily a huge problem for most research, but could clearly limit some use cases, especially if you need to understand what's in the video to be able to do your research. And there is a workaround though, and we're planning to add it. It's not in the crawler yet, but it's an open source project that's called InnerTube, and you will find this on GitHub. So the cool thing about InnerTube is it's a wrapper around an API. And so InnerTube leverages a public but undocumented YouTube API. The theory is with this API is that the smart TVs and other devices need to access YouTube without users being logged in. You know, if you go to YouTube on a smart TV, you still get presented with videos even if you're not authenticated. So this public API is available to be able to support those TVs. InnerTube taps into that to provide access to features that you can't get through the official data API, including transcriptions and things like related videos, which is important when you're trying to do research into what you may be offered up if you were looking at a specific video, what else you might get in terms of content. So we're looking to integrate this in the future to make the crawler even more powerful. But for now, let's talk about the deployment flexibility, because this was really important to me. I wanted people to be able to run this crawler basically anywhere, but also allow it to have sort of a cloud native deployment strategy to go with it. So we built support for multiple backends. First, both for development ease and also just so you can run it on a VM or on your laptop or whatever, there's local mode. You can literally run this on your laptop for testing or small scale crawls. That's a tongue twister. Secondly, we've got an Azure CLI backend, and this is for standard cloud operations where you want to scale up, specifically clearly inside of Azure, which is where we were deploying our cloud-based infrastructure. But the really cool one is Dapr. That, for anyone who hasn't come across it, is DAPR, and it's a microservices framework from the Linux Foundation. Dapr is awesome because it has plugins for a whole range of storage systems. So instead of me having to implement backends for every possible storage solution, Dapr handles that. You know, users can choose whatever storage they want, cloud storage, databases, basically you name it. You could even like post this stuff off to a pub/sub broker if you wanted to. The idea being that the application itself doesn't know nor care about the target system. This gives you incredible deployment flexibility, especially in things like Kubernetes environments, which is where Dapr is really targeted. But wait, I hear you all like on tenterhooks here, there is more. And so when it comes to storage, Dapr doesn't just handle storage, it also supports messaging protocols. And so this means instead of just persisting data to disk, you could send it to a message bus and then process it in real time. And so you think about this from a deployment perspective. You then have a crawler that's out there crawling Telegram, it's out there crawling YouTube. It gives us the ability to really hone in the flexibility and the performance when it comes to dealing with large amounts of data, especially with like multimedia, OCR, all that type of stuff. So for us, this was a game changer. We could send data directly to Databricks and have it processed almost instantly. Real-time data processing and streaming became a reality for the distributed crawler because of that connectivity. So imagine crawling social media and having data analyzed basically as it comes in. You don't have to batch it up. You don't have to wait for your crawl to run. As that data lands, you can put it in a bucket, you can create a trigger, you can create an event that instantly goes and processes that data for you. And so as you're working through that crawl, which may take hours, it may take days in some cases, it really means that you can obviously see what's coming in and work with it as it's arriving. Now, the final piece of the puzzle was creating a unified output format. Here's the insight. Every social media post fundamentally contains the same stuff. Text content, maybe some media, probably some media, engagement metrics. It's just the metadata around it that differs slightly between platforms. You know, if you're posting to TikTok, it's a video with some text. If you're posting to Instagram, maybe it's an image with some text. If you're posting to X, maybe it's some text, but it's probably still got an image or a video in it. You know, the same rules apply across all these different social media platforms. They just store text and multimedia data. So we based our format on a specification from Junkipedia, which is a standard they use across different social media sites. This meant consistent data structure regardless of source platform, easy ingestion into Databricks or other analytics tools, and we could even ingest Junkipedia's data if needed. And so this gave us a nice amount of flexibility around a standard that was already being used by a different organization that we were closely aligned with. Now, whether you're pulling from Telegram or YouTube or any future platform we add, the ETL process is the same. No more custom parsing for each platform. The output from each crawl, each post is the same, regardless of platform. And so that's the distributed crawler. And here's the best part. As part of my exit from the Accelerator, I was allowed to open source it. And so you can find it on GitHub. I'll post a link in the description. Right now it supports multiple backends, including Azure and Dapper, Telegram and YouTube platforms, and this unified output format. The real-time processing capabilities are there if you need them. The choice is yours. It really is flexible in the way that you want to be able to deploy this and use it in your own environment. And of course, there are many different social media platforms. There's also just the internet. And so we have plans to add more platforms over time. And we're looking to expand to other social media sites as probably standard website crawling as well. So if you're doing any kind of data research, web scraping or social media analysis, definitely check it out. It could save you a ton of time and effort. It's written in Golang, so if you know any Golang, feel free to go and poke around if you want to learn some more. I've heard Claude Code is very good at writing Golang for the distributed crawler. I hope you've enjoyed this. Thanks for watching. If you found it interesting, give it a thumbs up and let me know in the comments what platforms you'd like to see added next, because there are clearly a myriad of them. And I will see you in the next one.